Hi, thanks for joining me today. My name is George Donnelly. For those of you who don't know me, I've been a technical consultant for the Fuse Group since 2008. I'm honored to be here today, and I hope to be able to continue in this position for quite a time into the future. I want to talk to you a little bit about concrete moisture testing, specifically in situ relative humidity testing. And I've put some quotes around the words friend or foe because too many people are doing things incorrectly or interpreting them incorrectly, and we're going to try to help change that. Now, this is not a new subject, and I would suggest that I have put a follow-up to this on my website, moisturetesting.com. There's an essay that takes you all the way back to 1954 and the history of moisture testing and all the things that have been involved and how we got to the point we're at today. So for those who really want to understand the value of moisture testing and what it may or may not tell us, please feel free to do that. So why are we here today? So moisture testing of concrete floors is required by virtually every floor covering, floor coating, and floor covering adhesive manufacturer, regardless of the age or elevation of that floor slab. And I acknowledge that this requirement is known to most everyone working with floor coverings and coatings. However, understanding why tests are performed as they are and understanding the factors that affect test results may well mean the difference between floor covering installation success and failure. Too many decisions are based on test data alone without consideration of other pertinent factors. So what do failures look like? I'm not going to dwell on this. Sadly, you've probably all seen one, whether it's an emulsified adhesive, moisture condensate under carpet tile, discolored floor coverings, debonded epoxies, blisters in rubber. These are all problems that we don't want to have to deal with. These all happen to be new construct. On the other hand, we also see failures on old concrete, particularly where people go floor over floor. There's been a floor covering in place for many years. We decide that we don't need to do anything about it other than to install a new floor over it, and that floor fails. Probably the oldest photograph that I'm aware of a severe failure, this is attributable to Peter Craig in the bottom of the frame. This was a VAT floor held in place with solvent-based adhesives. Because it was down for 20 or 30 years, new VCT was installed with water-based adhesive. 90 days later, a total failure. So not a good thing. Now, did those photos show a floor covering failure? I'm going to argue today that the answer is no. The floor coverings, adhesives, and coatings were subjected to conditions that they were neither intended nor capable of dealing with. The floor systems failed the owner's intended use, and repairs were extremely expensive, but in fact, the concrete was either too wet when the floors were installed or became too wet sometime afterwards. So were the failures depicted in the slides preventable? Now the answer is yes. So two key objectives today are to ensure that you either perform or confirm proper moisture testing and become equipped to understand and evaluate the test result data. We talk for just really quickly, modern floor systems. I think everyone's aware that resilient floor covering is less permeable today than it was with older products, whether that's attributable to maintenance issues or asbestos. I think everyone recognizes that. We have many adhesives that are far more moisture sensitive than our old solvent-based adhesives. And I do recognize that we have high moisture adhesives, and we're going to talk a little bit about that. Resinous flooring is also far less permeable than the older coatings that we had, and generally carpet tiles are less permeable than broadloom carpet. Now, all of this is really to say that seeing an existing acceptable floor in place at a project is not an indication that a new floor covering can successfully be installed, and just relying on high moisture adhesives may not be the answer. Before we talk much about testing of concrete, it's always important to me to make sure that the audience that's listening to me is completely aware of the difference between concrete curing and concrete drying. I hear General contractors, flooring contractors, architects use these two words interchangeably, and they're not. They're diametrically opposed. Concrete cures by a chemical reaction to attain strength, and it's a process that requires as much water as is available. Concrete dries by evaporation, and it's important for you to know that fully dry concrete will attain in situ relative humidity closely matching the ambient condition. If there's a 50% relative humidity in the air, the concrete can attain 50% relative humidity. It can never be drier than that. But if it's wetter than that, there needs to be a question as to why. And finally, I see some installation booklets that still say that after 28 days you can install a floor because the concrete's cured. Well, maybe it is cured, but is it dry? No. So if we're going to talk about floor moisture analysis, I think we want to understand that we need to know what the moisture test is telling us. And to do that, we need to ask, where does the offending moisture come from? What are the hidden and or potential sources of a future problem? And have we considered all the factors that may affect our test results? So let's start with what I'll call moisture sources 1, and that's the residual concrete mix water. It takes about 3/10 of a pound of water to hydrate a pound of cement. At that point, we have something akin to Play-Doh. We couldn't do much with it. So common water cement ratios are going to be between 0.45 and 0.60. Becomes readily apparent even at 0.45, which is a good water cement ratio, we have 50% more water than we required in order to hydrate that cement. That's the water that we're going to want to dry out of the concrete. Why is it there? It's also called water of convenience. So that's what's going to let us transport, place, finish, and form the concrete. But other places that you may not be aware of, we look to lightweight aggregate concrete. That lightweight aggregate is typically what's poured on a deck, and the lightweight aggregate in the mix design will be in a saturated condition. That's typically going to be 10% to 30% of the reported weight actually being water, but not reported as water. Also has to dry, but is very slow. And then we see the use in parts of the country of limestone aggregate. And limestone aggregate can absorb 3 to 5% of its own weight in moisture. That's differentiated from granite or quartz, which are less than 0.5% of their own weight in moisture. So looking at that mix design and seeing limestone needs to tell us that this concrete is going to take longer to dry than something made with quartz or granite. And again, as I've just said, aggregate moisture content is typically not reported in the mix design. So if we look at moisture sources 2, this is what I'm going to call the content of a blotter course. Now, blotter courses aren't used as much today as they were in the past, but they were typically sand or granular fill or rock. This is the layer between the concrete and the vapor retarder. So under the concrete, but over the vapor retarder, and any moisture in there may be intentionally placed because we can't place concrete on dry sand. We have to wet it to gain compaction, or it could be accidentally placed by rain. I've actually been on sites where a vapor retarder was placed. We placed granular fill as a blotter course. It rained overnight. The next morning we're placing concrete, and we have to recognize that we now have a swimming pool liner full of wet granular fill that must dry through the concrete. It's going to take a long time. So it's fair to say that blotter courses are not common over the last 5 to 10 years, but older buildings may well have a blotter course. And if that blotter was rock, then I promise you that any vapor retarder that was placed is now full of holes because they dumped the rock on top of that plastic. The third place we need to look is the native subslab soil moisture content. And here's where an ineffective vapor retarder becomes a real problem. This is the native soil moisture, but it could be the result of irrigation, weather, trenching, plumbing. And we have data going all the way back to 1958 when the Academy of Sciences for the FHA studied soil under concrete floor slabs, and they found that regardless of the depth of the groundwater table, that 100% relative humidity directly beneath the slab was typically going to be found in soil, even under favorable drainage conditions. So I'm here to promise you that if the soil can reach 100%, the slab can reach 100%. And that's where a lot of our problems come from. When we talk then about subslab moisture control, there are times when you could be held responsible for knowing this information. ASTM E1745, which is the standard specification for plastic water vapor retarders used in contact with soil or granular fill under concrete slabs, was originally published in 1996 and updated in 2011. Arguably, that's not that long ago. So when we talk about looking particularly at older constructions, it's fair to say that any slab on ground construction prior to 2000 must be considered suspect. There's likely not an effective vapor retarder under it. Anything since 2000 still should be considered suspect. And the one thing I'll say emphatically is visqueen, if you see that in a specification, is not a vapor retarder. Typically it's clear plastic, and as this picture on the right shows, which is a Stego product, our high quality vapor retarders typically have color, Stego being yellow. Now, why it's important is ASTM F710, which is basically going to be listed in any project manual that you're going to look at, and is typically referenced in every installation guide that your floor covering or adhesive manufacturer is preparing, basically says that the installation of a permanent below slab vapor retarder meeting the requirements of E1745 is required for all new or on grade, new on or below grade, concrete floors over which resilient floorings are to be installed. So you need to ask and check and ensure that such a vapor retarder was in fact placed. Beyond the flooring industry, the American Concrete Institute has taken a position. In one of their guides, they are making the point that a moisture test should not be used to predict future concrete drying behavior, to provide evidence that moisture criteria are satisfied, or to establish expected floor covering performance if the concrete slab has not been placed directly on a vapor retarder or barrier. That's their wording. My caveat to that is that vapor retarder must be effective. It must meet ASTM E1745. So I think we also have to have a background knowledge of drying of concrete. And there are some rules of thumb that were published years ago by the Portland Cement Association. The first one is that hard rock concrete will dry at the approximate rate of 1 month per inch of thickness when air temperature is at least 70 degrees Fahrenheit, maximum relative humidity of 50%, and constant air movement. That doesn't happen very often. But if you've got 5 inches of concrete, it's probably going to need at least 5 months to dry under ideal conditions. If your GC calls you at 90 days and says, we need a floor installed, know that that concrete is not dry before you ever did any testing. Now, lightweight aggregate takes about 2 months per inch of thickness, and we've already touched on why, and that is that the lightweight aggregate contains a lot of water that has to slowly dry out of the concrete. And that lightweight aggregate concrete, and I think I said it earlier, is typically poured on a metal deck. I'm going to touch quickly then on ASTM flooring related standards that you need to be aware of. ASTM F710, we kind of touched on earlier. It's the suitability of concrete slabs for the installation of resilient flooring. And within it, we find those benchmark values of 3 pounds per 1,000 feet per 24 hours, or 75% relative humidity on an in situ test based on either a calcium chloride test or in situ relative humidity. So the calcium chloride test is F1869. The most recent publication date was in 2016. F2170, most recent publication was in 2019. I've used the word preferred after that test method because today it is. Years ago, we relied on calcium chloride. Pretty much every floor covering, adhesive, and coating manufacturer is listing the in situ test as either preferred or, in fact, the required test. But there should be an awareness that if you're going to use an electronic moisture meter, there is a standard practice for doing that, ASTM 2659. F2659. F3191 is now a water droplet test where we're going to look at the porosity of that concrete, decide whether we should consider it porous or non-porous. There's a test for the use of a surface RH hood, which has been withdrawn, but that hood is something that I use regularly when testing concrete that contains silicates and or if I'm testing the effectiveness of an epoxy membrane mitigation system. We can also see occasionally in specifications D4263, which is the old plastic sheet test. Clearly that does not develop enough information to make any kind of decisions from. And once in a while I still see E1907, which is a set of practices, but it is out of date and should be ignored. Test equipment, I'm sure everybody's seen. We have in situ relative humidity equipment, calcium chloride, impedance meters, pH strips, and on the right is that relative humidity hood that I often use. All right, so talking about the environment required then for that in situ relative humidity test. ASTM F2170 states concrete floor slabs shall be at service temperature in the occupied airspace above the floor slab shall be at service temperature and service relative humidity for at least 48 hours before making relative humidity measurements in the concrete slab. So if you're testing concrete relative humidity and the ambient air and the concrete temperature is 50 degrees, that test result may be interesting, but it's not actionable. I get reports regularly that show me concrete temperatures of 60 degrees, don't tell me anything about the ambient air, and tell me that they made a decision to use an adhesive or do something else, and it was not actionable data. Never should have been done. So let's talk about that in situ test. Okay, the test itself comes to us from Europe. It was studied at Lund University, and the intent of the test is to judge the dryness of new concrete and predict moisture equilibration of the slab after flooring is installed. Nothing more. It was never intended for use on concrete that's been re-wetted somehow, whether it's topical or bottom, never intended really for use on concrete that has no vapor retarder. So these pictorials are from their studies, and I'm going to focus on the bottom one for the moment because most of the work that is being done and most of the testing is being done on concrete that dries from one side only, whether it's sitting on a vapor retarder or on a metal deck. So what was learned through university study was that once concrete is placed, it's going to dry on a curve, and that if we place a sensor at 40% of the depth of that concrete, we're going to approximate what will occur after that moisture has equilibrated through the concrete as a result of placing a coating on top of the surface. Now, nobody has determined how long it takes for that equilibration to take place, but again, this is the intent of the test, nothing more. If we use it for other things, we need to consider other factors, and that's the big thing I want to get across to everyone. So ASTM F2170, again, says that those test wells are to be drilled to 40% of the slab thickness. That's 2 inches deep in 5 inches of concrete. On a suspended structural slab, which we didn't talk about, this is concrete drying from both sides, that test well should be drilled to 20% of the slab thickness. These are typically thicker slabs, so I can say an example, 1.4 inches in a 7-inch concrete slab. And then the suspended slab on a corrugated deck Again, this has been done incorrectly for a long time. It is now specifically written in F2170 that we are to drill to 40% of the thickest portion of the deck, regardless of where we drill the hole. So if we have corrugations that cause our concrete to be 3 inches thick over the corrugation, 5 inches at the bottom of the corrugation, we want the test well drilled to 2 inches, regardless of where on that slab we are drilling the holes. Also important, critically important, that all the dust and loose material must be vacuumed from that drilled test well. We need to be using a wire brush to ensure that all the loose material comes off the walls of that test well, and then we need to be able to vacuum to the bottom of that test well. Any dust in there is likely going to cause disruption of the ability of the probe to read the accurate relative humidity. Also, critical, the sensor inside the probe must be at temperature equilibrium with the concrete being tested. One probe manufacturer has noted that at even 90 degrees relative humidity, a 1 degree centigrade difference in temperature between the probe sensor and the concrete can result in a reported error of up to 5% plus or minus relative humidity. So you need to know that equilibration can take several hours, depending on the initial temperature of the probe and the concrete. You know, if you take probes out of a hot car and put them in cold concrete, that's going to be one thing. And conversely, probes out of a hot car into cooler concrete. So it's important, and I know there's at least one manufacturer, now maybe more, saying, oh, you can take a reading an hour after you've drilled the hole and inserted the probe. That is not actionable data. It may be qualitative, but it is not actionable. And I'll accept that if you're installing a highly sensitive floor that requires 75% relative humidity, and 1 hour into your test, you're reading 90% on one of these probes, I can promise it's not going to come down to 75. But again, it's actually qualitative, not quantitative. So again, we want to talk about that subslab vapor retarder. And it must be known, must be understood, that if there's not an effective vapor retarder beneath an on-grade or below-grade slab, any test performed for the purpose of establishing concrete dryness must be considered suspect and subject to change without notice. If additional moisture can enter the concrete from below, test data taken at any point with any test is no more than a picture in time. And I can tell you, I write a lot of test reports where I know there's no vapor retarder. It's been required that I do the test anyway. And right in my report, I state that without a vapor retarder, this data may be subject to change and could become invalid. Now, how do we establish the presence of that vapor retarder? Typically, we can find information on plans if it's new construct, or as I showed you, a lot of general contractors are now taking photographs of that vapor retarder to prove that they placed it. If that's not available, it may require coring to actually go look, or hopefully somebody's done some trenching on the project and we can observe at the edges of trenches whether a vapor retarder exists or not. But we need to know whether it's there and at what elevation. So if we start talking about how we're going to evaluate concrete dryness and really evaluate it, we need to know and document suitable ambient environment for testing. We need to know that there's a subslab vapor retarder. We want to know its quality and its elevation. Is it directly under the concrete? We do want that in situ relative humidity information because that is primary. And then we need to consider previously installed floor coverings, if applicable. We need to know if it's new construct, what the concrete aggregate type is. Is that going to affect our test results? And for high moisture tolerant adhesives, we need to be worried about the potential of dew point after occupancy. And we're going to talk about that for just a minute as we follow up on these things. So if we're going to have an action plan, I'm saying that with new construction, whether it's suspended concrete or slab on ground, underlain with that high quality vapor retarder, we can consider a high moisture adhesive. But I would have you question anything over 90%. And the reason for that question is that at 95% relative humidity, it takes a 2-degree Fahrenheit temperature shift to cross dew point. And if we cross dew point, we're going to turn relative humidity into liquid water. And once it's liquid water, guess what happened to all the warranties that were offered to you? They're gone because it's no longer relative humidity. So I would always consider mitigation for extremely moisture sensitive floor coverings. And frankly, unless I know how that building is going to be HVAC controlled, I would consider it for anything over 90%. But I understand if you have to use a high moisture adhesive without that ability to control temperature and humidity, understanding if you cross dew point, you may have a floor failure. When we look at remodel or reuse slab on ground without that E1745 vapor retarder, I am going to say mitigation is absolutely critical regardless of the RH test data and for all the reasons that I hope we've outlined today. So when we talk about in situ relative humidity testing as a friend or a foe, if it's properly performed and evaluated, concrete in situ relative humidity testing can be your friend. But if it's improperly performed or evaluated, this test will be your foe. Now, I think we've ended this a little bit beforehand, so I want to follow up and say we've covered a lot of information very quickly. This presentation should be available on the Fuse app, and it's my understanding it will also be on the Fuse library, so you can watch it again. But you can always call me, email me, or go through the forum with any questions on any of this. It's my job to try to help you, and I'm happy to do so. So with that, we're done here for today, and I thank you very much for your attention.